So in this video, we're going to talk about how to set up and use Grin's battery testing station, what we call our Grinspector. So the Grinspector has been released for a couple years now, but in 2020 we've made some nice updates to the software suite and some updates to the hardware itself so that it's an even more versatile tool for bike shops and hardcore DIYers who need to characterize and assess battery packs in the course of their business or daily operations. For Battery Grinspector, as you can see, is a simple station with a version 2 cycle analyst sitting on top of a control box underneath. What this control box does is let us manage the charging and discharging of a battery pack automatically through software control, so that you can push one button after plugging in your battery and charger in a load and have the battery be cycle charged and discharged as many times as you like with a nice printout graph of the results of those battery tests. So the Grinspector is something of a liaison between these different components. On the input side, we have a plug for the discharge port of the battery. So as soon as you plug in a battery to the Anderson labels that says battery, you see the Grinspector station powers up, and this is where it will discharge the battery from. If you're going to be using the Battery Grinspector for cycling the packs, you also need to charge through the Grinspector. And so the charging current passes through a separate plug. We use the 3-pin XLR standard, and that connects to the charging port of your battery pack. Now it's optional to hook up the battery this way. If you want to only do a discharge test but you don't care about charging it with the station, all you really need to hook up are the 2 discharge wires. Now for the battery test to take place, it has to discharge that battery and dump that energy somewhere. The Grinspector station doesn't have the means of absorbing the energy from a discharging battery. What it does is it puts the battery and hooks it up to the load plug that you see over here. And when you're testing a battery pack, you want something that can absorb the current and the power without overheating. And the simplest and most straightforward solution for a load is a basic power resistor. So this is what a typical power resistor might look like, a ceramic tube wrapped with a resistive element. You also see them with these extruded aluminum casings. We've also seen some shops that run a bunch of 12-volt light bulbs in series, hook up an old toaster, or improvise other creative discharge means. Our preference is these extruded aluminum load banks, battery loads, and we stock these in a 6.8 ohm 400 watt model. We chose this 6.8 ohm resistance because it's very convenient for the current levels you'd want to see when you're testing an e-bike battery. If you have a 36 volt battery, one 6.8 ohm load results in a 5 amp discharge. If you put 2 of these loads in parallel, you'll have 10 amps, but 4 of them in parallel, you'll have 20 amps. With a 48 volt pack, you get 7.5 amps for each load that's connected, and with a 52 volt pack, it's closer to 8 amps. One thing to note about a resistor like this, even though this is rated for 400 watts, it will get extremely hot during that 400 watt discharge. So if you have just a simple resistor, don't let this sit on a piece of paper or wooden bench or something. You want to make sure this is mounted on some insulated high temperature surface, because it will get scalding hot to the touch even when you're using the resistor within its ratings. If you're doing lots of battery testing, you'll find our dual load banks here to be super convenient. What we've done in this is mounted 2 of those 400 watt 6.8 ohm resistors inside a stainless steel chassis that acts both as a heat shield and a chimney. So when these resistors are generating heat, the air gets hot and moves upwards out the vents at the top. That sucks some cool air from below and enables the casing to stay warm to the touch even when this thing's running at maximum power. And we've very conveniently wired up those 2 resistors with a rotary switch that lets us switch between connections in series, in parallel, or independently, so that we can have a low, a medium, and a high discharge current at the simple flip of a switch without having to unplug and replug those resistors in series or parallel. So in our lowest setting, this load will do 2.5 amps on a 36 volt pack, 3.5 amps with 48 volts. Does double that in the medium setting, 5 amps and 7 amps, and double that again in the highest setting for 10 amps and 14 amps. This will work up to 52 volt battery packs, no problem. If you want to test 72 volt batteries, then you must have this in the low setting. If you run 72 volts in either of the other settings, you will burn up and overheat the resistors and make a stinky mess. But in the low setting, this will do a 5 amp discharge with a 72 volt battery pack. So to complete the hookup of our Grinspector station, we're going to attach our load to the load port, and we're also going to connect the battery charger to the charging port. So here I have a satiator charger that's very convenient because we can now switch to different profiles depending on which battery we're testing. Otherwise, you would use the same charger that you have that comes with the battery pack, and if it's not using an XLR plug, you would simply have adapter cables from XLR to the different charging port standards that you use in your shop. So there's 2 more connections to the Grinspector that are required. We've done all the hardware. for doing the discharge and the charging, but there's two connections to the computer. So we have one plug here, which is the TRRS communication plug. So this is a standard connection for communicating with the cycle analyst, and that's what's necessary to log all the data on a computer. So it's very, very important that we plug in a TRRS cable to the Grinspector communication port. There's another USB plug that you can connect, which is somewhat more optional. This is a USB 12-volt adapter. What it does is it takes the 5 volts from the USB port and steps that up to 12 volts in order to keep the station powered up even if the battery is disconnected. So remember, when I plugged in the battery, it immediately turned on and showed us 53 volts, but if I was to unplug the battery, the station shuts off. What that means, if we're doing a discharge test, if you discharge the battery to the point that the battery shuts off, then the whole station will turn on and it won't have the ability to begin a charging cycle afterwards. So if you're cycling the batteries up and down, you want to plug in the auxiliary 12-volt power supply, and that will boot up the Grinspector even if the battery pack is disconnected and allow the cycle test to continue unimpeded. Okay, now that we've got all the components plugged in here, we're going to show you how to set up our software for doing a basic discharge test, and then we'll show you how to set up profiles to do multiple discharges on multiple different styles of battery pack. So the software is freely available from our website. If you go to ebike.ca, product information, and then you can choose the Grinspector product. There's a section here on the software. And then from the software, you click one link to download the software application. This is available, it says now, for Windows only. We have it now available for Windows, Mac OS, and Linux. And then that software, you unzip it onto your computer, and then you launch grinspector.exe. And this here is what the test station looks like when it's first booted up. And at the moment, there's no test station set up for the software. So we can see we'll have a plane over on the right side with the graphs, and on the left side here is the status for each test station. So here we're going to add our Grinspector. So when we plugged in the USB cable, it created a communications port on the device settings of this computer. And on this computer, that's the only COM port present. And you can see that it says test station number 4. We're going to talk about station IDs a bit later in the video, but that corresponds to this Grinspector, which you can see is ID number 4. This is in case you're running a bank of battery testers. So if you're a shop that processes many batteries in a day, you can have 2, 3, 4, 5, as many Grinspectors as you like, all running on the same software, all running simultaneously, and be able to easily identify which battery station corresponds to which graphs that you see on the software here. So now we've added station 4 to the Grinspector software suite, and now we can set up all the parameters for a test. So typically you'd want to identify the serial number of the battery pack. The battery that I've got here is a random shop pack. You can see that it was originally a 10 amp hour 48 volt lithium battery. Last time it was tested a long time ago, it gave 8 amp hours. This has been sitting around our shop for years and years, so we're going to do an updated test and see what's the status of this old battery, and is it even worth us having around, or is it at a point where we should probably recycle it. And on the back, most battery packs will have a serial number somewhere, so this one is DLG 4810 12C00 something other, so that can be typed in here, DLG 4810 and 12C00055. Okay, and the importance of putting the serial number, of course, is so that you can identify test results and correlate them to the battery pack down the road. And so now here's where we set up the test parameters that we want in this test. So in this case here, we can choose how many times we charge and discharge the battery pack. That's what the number of cycles is. And we're going to do just a simple discharge test for this first one. So we're just going to discharge the battery once and then partly charge it afterwards, and that'll be the end of the test. The maximum charge time, if you are doing multiple cycles, this is the duration that it will continue to allow the battery to charge before it switches over to discharging. So you have to make sure that's long enough to account for a full charge in the battery after it's been fully depleted. There's an optional field here for a low voltage cutoff. So on a 48 volt battery, you typically would want to discharge it to about 40 volts to get the battery all the way flat. If you want to confirm that the battery management circuit works, you could set that to a lower value, let's say 35 volts. And at 35 volts, the battery BMS should really shut off. If you see the discharge graph go all the way down to 35 volts, then this testing has confirmed that the BMS circuit isn't doing its job. And that would be another thing you'd want to check if you're assessing the health or status of an old random battery in the shop. Now this final voltage parameter is an interesting one. When the final discharge cycle has been completed, the Grinspector station connects the charger, but it doesn't allow it to charge all the way up for the full charge time if you set a final charge voltage to stop the charging early. The reason for doing this is that the shipping of lithium batteries is heavily regulated, and they require that you have the battery at 30% charge level before you ship it. So this gives a very convenient way of preparing a battery, not only to characterize it, but to have it in a state where you can ship it back to a customer. So in a 48 volt battery, if you just put 48 volts as the final charge voltage, if you stop the charging once it hits 48 volts, the battery will be at about 47 volts, which is right around the 30% charge level. On the fields on the right are a little bit more advanced, but this one here, measure RBAC, this is a new feature in our 2020 version of the Grinspector software suite, and this allows the station itself to assess the internal resistance of the battery periodically during the discharge. It does that by pausing the discharge current for a short amount of time and seeing how much the voltage rebounds and then drops down again when the discharge current is enabled. And by looking at that change in voltage that you get, knowing the change in current that flows, it can estimate the internal resistance of the cells, and that's an incredibly useful data point for assessing the health of the battery. But you'll find with older batteries, as they age, their capacity might decrease a little bit, but you get a noticeable increase in the internal resistance of the cells, and can have a better assessment on where the battery is in its lifespan by having that information. So here it's set up to do that test every half amp hour during the discharge. And that is all we need to do. We could give a name if we wanted to save this test, so I might call this a garage 48 volt easy, and now we can start our test. So when I hit start, you'll see that it initially starts off charging, and it's going to attempt to charge. It'll leave the charger connected for up to 12 hours, because we set 12 hours as the maximum charge time here. The Grinspector station can't actually measure how much charging current is flowing. It only sees the voltage that's present during the charging process. In this case here, we know that this battery is already almost fully charged, so it's sitting at 54.5 volts. 54.6 volts is a full charge voltage, and there's only, well, that is actually 4 amps of current flowing in. So we're going to allow this to sit until that current trickles down more to like 0.2 or 0.3 amps, and then once we see it at that lower current, we're going to hit skip so we don't wait the whole 12 hours, and then the station will jump to the discharging. Now while it's charging, we're going to make sure that we have the rest of the stuff configured as we want it. So I've connected the load to our dual load bank, and right now I'm set to the low discharge current, which is going to be 3.5 amps for a 48 volt pack. And that's a pretty low current to validate a battery, because on an e-bike you're usually doing 10 to 20 amps of current. So it makes more sense if you're trying to assess if a battery is suitable for use on a bike to switch it up to a higher current. So I'm actually going to go all the way to 14 amps in this test, because if this battery can't deliver a 14 amp discharge, then it's pretty much useless to use on an e-bike pack. So now we can see that the battery charger is pretty much fully charged. We're down to 0.2 amps on the satiator. So we're going to skip the rest of this charging because it's effectively fully charged and begin the discharge. So this is a convenient way of just moving the test along rather than having things pause, take unnecessarily long. And now the moment that this skips, you can see, so now as the battery pack's discharging, the Grinspector station shows on the top here that it's in discharge mode. We can see there's 14.5 amps of current flowing through the load bank, and we have an accumulating run of the total watt hours and amp hours that have been discharged from the battery pack up to that point. Meanwhile, over at our computer, we can see that we're now starting to generate a discharge block. So the top graph here is showing a real-time readout of the voltage of the battery pack, and the bottom one here shows the discharging current. So the current is up at over 14 amps, the voltage is over 50 volts, and is slowly going down. So as this test continues, you're going to see the amp hour scale continue to shift to larger and larger amp hours, and the voltage goes down, and we'll see at what voltage the battery pack finally shuts off and how many amp hours we got out of it. We're also going to notice every 0.5 amp hours of discharging, the current's going to stop briefly, and you'll see the Grinspector station is going to say it's going to switch to off and then to discharge, and you'll see a little status update on the station here is saying that it's doing a battery resistance measurement. So right now we're at 0.36 amp hours, 0.37. We're just going to wait a little bit longer, and then you'll get to witness one of these battery internal resistance measures. The second graph here I showed, this is showing the discharging current. We can change it so that that second graph is an actual readout or display of the battery resistance test. Up to this point, there's been no battery resistance test so far, so there's no graph to see, but that will change once we get to 0.5 amp hours, which is coming up imminently. Okay, and here we go. So now you can see IR test, recovering from IR test, and then it will resume. The recovery is to allow the voltages to equalize a little bit so that you don't see a blip in the graph when that test took place. And now you can see that we have milliohm resistance in our test summary. So that test showed 213 milliohms for the battery internal resistance. And if we switched over on this display chart, we'll see this one data point here of just over 200 milliohms. So now we're just going to wait for this whole test to run its course and then make some decisions about whether we test the battery further, take it away to the recycling yards, or donate it to a good cause. So now that test is wrapped up a little sooner than expected. So if you look here, we can see the plot of our discharge curve, and all we got from this battery pack was 3.4 amp hours before the BMS circuit shut off. If we look at the battery's internal resistance data, you can see that as it discharged, the internal resistance kept increasing, and it was over almost 350 milliohms at the point of the cutoff. So this is a good example of using the Grinspector QC station in order to identify an unknown battery and see if it's worth putting any effort into or not. Here, considering we only got 3.4 amp hours out of the pack, I would consider it to be basically a write-off, a battery subject to recycling. What the Grinspector can do now at this stage is generate a PDF print report of this discharge test. So if you click this Generate PDF button, that'll automatically generate a summary of the test results. So here we only did one discharge. It gave us just 150 watt hours, 3.4 amp hours, and you can see here that it cut off. And the point of the cutoff, the battery was at about 40 volts. So we know it's not just one cell that was bad during this time, but the entire pack showing low capacity. If we saw that the voltage was sitting maybe 48 volts or 46 volts when the BMS shut off, then it might be worthwhile to open this battery pack and try to identify a single cell group that might be responsible for the shutdown. But here we can see we just have a battery that's really end of life. And we can also tell that from this average internal resistance data, close to 300 milliohms, whereas when this battery pack was new, the internal resistance was more like 150 to 180 milliohms. So now this PDF can be conveniently printed and then included as a test report with the battery. So if you want to run the Grinspector as a battery testing service, you can have a nice official looking test results to show for it. If you run a test and later on, say we want to repeat this test, but instead of doing the discharge at, as you can see, 12.5 amps was our average discharge current. If we wanted to run a test maybe at 2 or 3 amps to see if we can eke more amp hours out of it, I could start a new test and then append the test data to this previous test. And then if you want to load a previous test result, you can always add a test station and then add a preview-only station. And this will let us open a pane for the Grinspector where we just get to load a previous test file. So here, for example, I could load a test file from a previous battery experiment. Here I'm going to look at a 36 volt, 16.5 amp hour battery. And then we're able to restore all the data from that last experiment, and now you can see a more typical set of discharge curve. So here we're getting close to 17 amp hours from this 36 volt battery pack, and this test, you can see we actually did multiple discharges on. So if I want to show only the results of this preview log, I could hide station 4. Now all we're looking at are these tests. And this graph pane, you notice as I hover over it, it shows me the value at that point. So I can see that here I was 12.76 amp hours at 34 volts. You can zoom in on the graph if you want to highlight any specific information and get data points to looking at one specific area, cancel the zoom to view the whole thing. And now if we wanted to generate a PDF of this previous log file, we'd again click this Generate PDF button, and now we can see 4 different discharges that have taken place and the test results on each of those. So you can see here the first discharge was at 4.5 amps, then closer to 10 amps, then closer to 18 amps for the final 2 discharges. And then you can see how many watt hours the battery gives at those different kind of discharge currents. So you can see just over 612 watt hours at a low current, 580 some odd when you discharge it at a higher rate, but it still gives pretty much the full capacity, 17 amp hours, even at those higher discharge currents. And then you can see the internal resistance of this battery is quite a bit lower, averaging more like 100 milliohms, as opposed to the battery that you just saw there that was, close to 300 milliohms, which means a lot more voltage sag when you draw high currents. So that summarizes the basic setup and usage of a Grinspector for testing a battery. As I said in the video, you can have multiple stations all running simultaneously with the same software, and we may do a little video tour of our own QC station here at Grin where we test up to 5 battery packs at a time.